Hi everyone, I'm Haojun, a third-year PhD student at University of Sydney. Welcome to our talk. Today, I will present our work on LLM inference with 6-bit quantization. This work is a joint effort between the research teams at University of Sydney and Microsoft DeepSpeed. As we can tell from the name, large language models are extremely large regarding model parameter size, while a state-of-the-art GPUs can at most have 80 gigabytes SPM. The model parameters of a LLM can easily be larger than 100 gigabytes. Thus, serving LLM inference is like putting an elephant into the fridge. Well, to fit LLMs to GPUs more easily, model quantization is widely adopted to compress the model size. For our case, which is weight-only quantization, fewer bits are used to represent each model weight, resulting in more compact representation of the model. As you can see in the figure, these are the data types that are officially supported by NVIDIA H100 GPUs. Besides, there is already several software support for 4-bit weight-only quantization. Well, although 4-bit quantization can do a better job in model size reduction, it's also more likely to reduce the model quality. On the other hand, 8-bit quantization is not as efficient as 4-bit in reducing the model size. But why does the research community only consider 4 and 8-bit quantization in LLM inference? One possible reason is that there is no efficient system support for quantization other than 4 and 8 bits. Even if they succeeded in quantizing LLM to 6-bit or 5-bit with negligible accuracy loss, they might not be able to run the model inference as fast as the FP6-Centric, not to mention to get faster. It has motivated us to exploring more choices for weight quantization for large language models. We have found that 6-bit is an overlooked sweet spot for LLM quantization, where superior trade-offs between inference cost and model quality can be achieved. We tried different bit widths, goes from 16-bit baseline to the 4-bit to quantize the model. And the largest bit width we can achieve is 6-bit, where the accuracy drop compared to FP16 is negligible. Let's first evaluate how FP6 works regarding the zero-shot perplexity. Well, zero-shot means the model is directly performing a task without any examples, which is the lower, the better. As shown in the table, int4 quantization causes more model quality degradations. In contrast, our FP6 can achieve lossless model compression, where the perplexity of Llama 65B only increases by 0.01. We also examined the capability of FP6 beyond the zero-shot perplexity. Specifically, we evaluated the model quality on code generation. Pass at 1 means for each input problem, we generate one code example using LLM. And the values in the table describes the percentage of cases where the generated code is correct. Thus, the pass at 1 is the higher the better. We can tell from the table that FP6 quantization is constantly better than int4 and is very close to the FP16 baseline. We have already compared our FP6 with int4. On the other hand, FP6 can do a better job than FP16 and int8. Firstly, we can more effectively reduce model size, thus reducing the number of GPUs required to serve a given LLM. For example, we can serve Llama 70B with a single A100 GPU. Besides, we can achieve faster execution of linear layers shown in the figure, which is more which is the most time-consuming part during the token generation. Till now, we have identified that FP6 quantization as a promising way to deploy LLMs. However, there is no efficient system support for the 6-bit execution on modern GPUs, especially on tensor cores. Motivated by this observation, we proposed TC-FPX. The TC means a tensor core, FPX means arbitrary bitwise of the flow point. We propose the first full-stack GPU system design with unified tensor core support for various quantization bitwise. For example, we can support FPX quantization on A100 GPUs, which is not natively supported by the GPU hardware. It is also not supported by the H100. But before going into more details of our kernel designs, I'd like to describe the high-level design choices we have made. The first design choice is, should we perform WXA16 computation using two separate GPU kernels or a single GPU kernel? The straightforward solution is shown on the left, where an extra GPU kernel is added before the normal W16A16 kernel, like a Kubla's kernel. We call this extra kernel the dequantization kernel, which transforms the FPX weights back to FP16. However, it would be even slower than the FP16 baseline for LLM decoding because the FP16 weight would be first returned and then will be first returned to and then be read from the GPU DRAM. As shown on the right, it's more efficient to fuse the dequantization and the matrix multiplication process into a single GPU kernel, eliminating the read and write of the FP16 weights. The second design choice is, how do we perform the matrix multiplication? As shown in the right figure, we can perform the matrix multiplication with either general purpose FP32 cores, aka the SIMT cores, or we can use a dedicated hardware called tensor cores. Our conclusion is clear that it is necessary to use tensor cores. As shown in the left figure, we have benchmarked an existing kernel designs and disable its tensor core usage. And we can find that its scalability across different batch sizes is very poor. However, it is challenging to design such a single GPU kernel with tensor cores enabled. For example, the memory access pattern would be hardware unfriendly if we want to support such irregular bitwise. For example, it's not a power of 2. We call it irregular on tensor cores. First of all, modern GPU memory systems do not naturally support irregular bitwise. The complex data layout requirements of tensor cores make it even more challenging. Due to the time limit here, please refer to our paper for more details here. And we propose ahead of time prepacking to solve this challenge. The insights is that the complicated memory layout transformation can be applied to the weights ahead of time and introduce no runtime overhead because the model weights are statically fixed after the model is trained and quantized. In general, weight prepacking consists of 4 steps. In the first step, we're gathering all the weights leaded by each GPU thread and combine these weights. The weights picked for each thread are then combined locally in a relative temporary order as they will be consumed by the tensor cores. In the second step, we split each weights into several segments, and we make sure that each segment is a regular bitwise, like 1 bit, 2 bit, or 4 bits, which is a power of 2. In the third step, we combine all the weights leaded by the whole GPU warp into a unified linear memory space. And in the final step, we perform bit-level reordering for efficiency purpose. And the second challenge is that reconstructing the FP16 weights during runtime might cause high runtime overhead. As shown in the right figure, the X bit weights will be loaded to register and transformed to equivalent FP16 value before we feed this value to the tensor core. Thus, we propose our SIMT-efficient GPU runtime to minimize the runtime overhead. The transformation from FPX to FP16 consists of two steps. In the first step, we compose the segments together and recover the X-bit weights, which is decomposed during the weight prepacking phase. So in the second step, we need to dequantize the X-bit weight to FP16 data type. Both steps can be very computationally expensive. We will first talk about the process of weight composition. The FP6 weights are decomposed into two segments by our ahead-of-time prepacking. Thus, we store their 2-bit segments and their 4-bit segments with two different sets of registers in runtime, as shown in the right figure. To reduce the runtime overhead, we propose to exploit the bit-level parallelism within each 32-bit register. Specifically, each register can be treated as 4 processing slots, and each slot working with the same SIMT core instruction but process different input data. In this way, the SIMT instructions can be reduced by 4 times. Given that these segments have regular bit widths, so this process can become very efficient. As for the weight dequantization, the major difficulty here is that we need to manipulate the new exponent field. As we can tell from the equation here, the exponential bias for FP16 and FP6 is different. Thus, the straightforward way is to calculate the new exponent of FP16 by adding a constant value to the old exponent. The constant value here is 12 for FP6. However, it requires expensive bitwise operations to manipulate such field. We found that this dequantization process can be effectively simplified if we ignore the differences in bias when we cast the FPX weights to the FP16. Instead, we multiply the generated FP16 value with the FP16 constant value to maintain the correctness after that. With the optimization proposed in the last slides, the dequantization process becomes extremely simple, which only requires bit-level shifting and copy. To further reduce the runtime overhead, we also apply bit-level parallelism here. In total, only 7 bit-level operations are required to dequantize 4 FP6 weights during runtime. We evaluate the performance at 2 levels: kernel-level benchmarking and model-level inference using deep speed integration. Here are the key setups. And as for the results, we evaluate the performance of TC-FPX kernel on linear layers on the different shapes from real models. On average, our FPX kernel outperforms bits and bytes, cuBLAS, and TensorRT-LLM significantly if 6-bit quantization is applied. And even higher speed up can be achieved if we use FP5. Here are the end-to-end performance comparison on Llama 70B. 2 A100 GPUs are used for the inference of FP16 baseline. since the model weights cannot be fit into a single GPU. The results show that our FP6 can achieve higher normalized inference throughput than the FP16 baseline. Besides, our FP6 can serve at most 32 requests, while the Intel 8 baseline can only serve 8 requests simultaneously. The latency breakdown is shown in the right figure. Given that 2 GPUs are used in the FP16 baseline, the execution time on both GPUs is counted in this figure. Our execution of linear layer is the fastest among all 3 because the adoption of our TC-FPX kernel. Besides, the cross-GPU communications is fully avoided if in FP6 inference, since only a single GPU is required in our case. Similar results can be found in the inference of OPT30B models. Well, before wrapping up this talk, I'd like to show you more implementation details of this work. Well, our GPU kernels is implemented with CUDA code, which provide both C++ and PyTorch APIs and can be easily integrated into other inference systems. Our code is fully templated, and so that different combinations of exponent and mantissa bitwise are supported. For example, we can support FP6 E3 M2, FP6 E2 M3, or FP5 E2 M2. Our kernel code is open sourced, and you can try our end-to-end FP6 inference using the inference framework DeepSpeed. So our work is already integrated in there, so you can directly use it. What's more, our kernel is also adopted by the PyTorch architecture optimization repo. They integrated our kernel as a cutting-edge quantization methods. Well, in summary, FP6 quantization is a practical option to democratize the deployment of LLMs without significantly sacrifice the model quality. Here are the summarized contribution of this work. It's also worth noting that our design methods is generic enough to be applied to more GPU architectures, not limited to Ampere, but also can be applied to Hopper or Volta GPUs. Well, thanks for listening to my talk, and I'm happy to answer any questions. Thank you.